Okay, so I guess we will start now, so welcome back. We will now have a guest lecture on Morphological Computational Control, Abstract Concepts and Future Applications in Medicine by Rudolf Fischlin from the Zurich University of Applied Sciences. He's, among other things, a member of the board of directors of the ECLT in Venice. He's an expert on morphological computation, and among others, is one of the co-editors of a book, e-book on opinions and outlooks on morphological computation that we link to on the website. Looking forward to your talk, and I pass the floor to you.
So, thank you very much for the kind introduction. First, I would like to thank you for giving me the opportunity to present certain ideas and aspects of our research. I just want, I have to, so here, it's a little bit new technology for me. I want to start with a little bit of motivation. I think you all know pictures like this. Here you see a picture from the Soccer World Cup of Robot Soccer World Cup 2008 and two ballet dancers. And I think it's quite obvious that 50 years of research in the construction of walking machines had not yet resulted in something which is only slightly comparable to what compliant biological systems as we humans are can do. So why is that? Is there a lack of computational power? Is there not enough sensor, or what? Well, of course there were many attempts to increase the control and the computational power, but there is also, as you may know quite well, another direction, a direction that has been pioneered by Rolf Pfeiffer, embodied intelligence, the idea that control is not only performed by whatever type of digital control unit, but a part of the control is outsourced to the dynamics of the physical body that is controlled, or that has to be controlled. So, how can that work? Oops, I have a technical problem here. How can that work? Well, let's take a very simple example. Here you see a horse. Horses do have different gait patterns, and how can a horse control its gaits? Well, one possible explanation, probably a slightly oversimplified one, but that shall illustrate how the body can interact or support control, is to regard the body as just a physical dynamical system. And at the end, a horse's body is a physical system, and therefore it has sort of an attractor landscape that governs its movement. So here you see an illustration of, or an abstract illustration of such an attractor landscape. It contains, for here, only two limit cycles, but the picture is intended to illustrate the division of labor between the brain and the body. Well, the brain in this picture only has to choose the basin of attraction. Once you have brought your system into a basin of attraction that contains a limit cycle which leads to a gait pattern or another type of movement pattern that you desire, the dynamics of the body takes over all the details of the control of the process. A small perturbation does not really affect the movement. The movement will go back on the limit cycle. Well, that's the idea of an attractor. Of course, this picture as it's drawn here is quite incomplete. That idea of division of work of labor only works if transient times are short, if fluctuations are damped out readily, and this is, I think, the most important aspect, if this attractor landscape can be modified and adapted to external conditions. At the end, what we are doing when we learn something new is we change our attractor landscape. And in fact, and I think that's quite an important insight from people like Thomas Schack and Helge Ritter. Thomas Schack always tells me that what you're doing when you learn a new sport, and I'm not a very good ski driver, but I know a little bit how to ski. So what you learn when you improve your skiing skills is not how to react to specific bumps, but what you're doing is you learn how to bring your body into a posture and into, let's say, a state, internal tensions, also the shape, into a state such that if there is a bump, it is easy to react on this bump. So that's actually what you learn when you learn something new in sport. How to bring your body into a position, into a state that it is easy to react on, well, the, let's say, perturbations or the requirements that are posed by the environment. So, now, why do we call it morphological computation, or in case of a robot, morphological control? Well, this claim is based on a, I would say, very important paper by Helmut Hauser. Helmut Hauser proved that a sufficiently complex master spring system equipped with a very simple, in this case that he investigated a feed-forward neural network, with a very simple control unit, is able of generating a really large class of different movement patterns, of different, well, different functions. Actually, such a system can be understood as a mapping, well, in a mathematical sense, a mapping that generates upon small or a given input signal that generates a large class of possible output patterns. And therefore, not just because you have a system that is able of, let's say, generating 3 or 4 different patterns, but because you have the possibility to tune it such that a very large class of movement patterns can be generated. Therefore, we speak of morphological computation and control. A sufficiently complex body is able of transforming input functions into output functions, and this in a rather general sense. I have to be honest here, the picture of limit cycles is not absolutely adequate when it comes to the work of Helmut Hauser. As a matter of fact, if you want to delve deeper into his research, you have to be acquainted, or to make you acquainted with the concept of reservoir computing. That's the theoretical idea behind his work. So the important thing, the reason why human beings can work so well, or can walk so well, compared to robot, is then not that our brains are so much smarter than the control units of a robot, but because our body makes walking comparably easy. That's the message here. The body supports, for example, processes like walking. So, before I go into the application field, I would like to delve a little bit deeper into some fundamental consideration concerning control of robots. First, I have to explain something, I think, which is something very important. When we speak about morphology, sometimes people think morphology is only the geometry, the shape of the object. Here, to make that clear, by the term morphology, we always understand shape, geometry, plus material properties such as elasticity modules, friction coefficients, weight, and so on and so forth. Morphology is shape plus material properties. So, question to the audience. How do you control a robot? It's a conventional task. Okay, maybe you will do it a little in a much more sophisticated manner, but let's assume that conventionally you want to build a robot. How do you control it? Yeah, it's a very,
yeah, you can write a control program.
Exactly. A control program. What is a control program, or what does a control program do? Well, here's the ideal situation of a robot, of controlling a robot. The robot is equipped with a couple of sensors. These sensors determine the precise state of the robot. From this precise state, you generate an abstract representation of the robot, and using this abstract representation, by virtue of a kinematic model, you plan your next step. As soon as you have an output of your computation, which takes place in, so to say, the space of the representation, this result is translated back into signals that, into commands that are sent to the actuators of your robot, and you do something. Of course, this point of view or this perspective is an ideal one. As a matter of fact, in reality, what happens is that you always have to cope with what engineers or physicists would call physical noise. You may not be able to determine precisely the state of the robot. There may be external influences of whatever kind. So what you have to cope with is noise. Noise that results from the physical dynamics of your system. Well, good conventional engineering tries to reduce this physical noise. Morphological computation and control tries it the other way around. Morphological computation tries to exploit the physical dynamics of the system to maximize its benefit for computation, for control, and to reduce the amount of computation you have to perform in an external or, if you like, a digital control unit. And here on this slide you see I have chosen deliberately a feed-formal neural network as a controller. You see that the work of Helmut Hauser shows that the sufficiently rich and complex dynamics plus a feed-formal neural network can do more or less the same as a conventional controller can do. So, designing a system that its limit cycles perform the desired movement patterns, you could call that simply good engineering. So why do we call it morphological computation and control? Or what is really new with that? Or what, well, at least is some sort of new. Well, first, softness. Here you see a tentative robot. I think you all know Roboy. Then you're probably familiar with the Octopus project from the AI lab in Zurich. There are also other soft robot groups. Of course, here I've shown only very few results. There are many, many more. Here you see results from George Whiteside's lab. What morphological computation and control allows you is to introduce softness into robotics. So, conventional robots in a plant, in a factory, robots are usually heavy and stiff. So, why are they heavy and stiff? Why are robots heavy and stiff? Well, answer is relatively easy. What is the essence of stiffness? Well, the essence of stiffness means that you have only very few parameters that determine the full state of the system, and you have complete control over these parameters. A soft system, let's say a soft system, needs to be described by many states. If you want to describe the precise shape of a cushion, for example, you need quite a lot of parameters. So soft systems are governed or are determined by many degrees of freedom. And of course, many degrees of freedom, in order to determine them, that requires a lot of actuators and a lot of sensors. And that's not what you usually do in conventional robotics and in conventional engineering. So with respect to your geometry, softness means many parameters, stiffness means few parameters. And to some extent, you can say the same about heavy weight. Heavy weight means localization in momentum space. That has nothing whatsoever to do with quantum mechanics, of course. When I say that stiffness means localization in real space, then what I want to say is that only a few parameters determine precisely the state of a robot. Well, heavy weight means that's pure physics, that if a robot interacts with an object, for example, it lifts an object, something like that, as long as this object is very lightweighted, the momentum the robot is not affected if the robot is heavy. So a heavy system is in that respect easier to control, just because the interaction with the object to move is not that important, just for physical reasons. So what is now the benefit of morphological computation and control? Well, in contrast to conventional engineering, morphological computation and control does not require knowledge of does not require perfect knowledge of the state of a robot. So it's generically not necessary to do so. So, because it's generically not necessary to have complete knowledge of the system, if you apply morphological computation, it is possible to use morphological computation and control for controlling also soft and light-weighted systems. There's another aspect. Usually when we speak about robots, we speak about systems that are governed by classical mechanics. That's okay. But there are a lot of systems, important systems, especially in medicine, which are governed not by classical but by statistical mechanics. As soon as chemistry enters the scene, chemistry is generically governed by statistical mechanics. So we introduced the concept of embodied, or the term embodied process control, thereby meaning that embodied process control relates to statistical mechanics as embodied intelligence relates to classical mechanics. Probably it's a little bit a superfluous term. Nevertheless, what we want to highlight is that the ideas of embodied intelligence also can be used in systems which are not classically understood or which are not understood in terms of classical mechanics. So, do you know a system that performs complicated, information-intensive tasks, but is governed by statistical mechanics? You are composed of these systems. These systems are called cells. Here, for example, you see a macrophage. This macrophage does something very demanding. It distinguishes between self and non-self, and what you're seeing here is best described by the term the kiss of death. This guy here, the bluish guy here, is gone, I can tell you. So, this macrophage governed purely on chemical processes, therefore heavily influenced and heavily determined by statistical mechanics, can distinguish self and non-self, and if there is non-self, it can take, well, appropriate action, as it is said in the movies. So, now I want to show you some ideas towards application of these ideas. First, the slogan of our first application is, we can't rejuvenate your body, but maybe we are able to rejuvenate your attractor landscape. As a matter of fact, when you get older, you start to experience certain difficulties in performing precise movements. Maybe not at 50, maybe not at 60, but when you're getting older, 80 or something like that, you really become you're really experiencing troubles when you, for example, want to dance or doing something like that. So why is that? The conventional explanation for this, well, decrease of control is that your brain's capabilities decrease with age. Also, this is true. One has to say that the brain seems to be surprisingly robust against aging processes. It's probably not really the brain that causes the problem. It may be the body. If you assume that the physical dynamics of your body supports control, well, then it becomes plausible that aging processes, which, for example, change the elasticity of your sinews and the strength of your muscles and your joints and whatever bodily parts may be affected, that changing the properties of these body parts affects the whole dynamics of the body, and therefore renders or results in a fitness landscape which is not as supportive as it used to be when it was when your body was 20 for the purpose of controlling complicated movements. To some extent, this is good news, because we can't of course, make your sinews again as elastic we may not give your sinews back the elasticity they had when they were 20, but we can on a global level, by the application of external means, for example by the application of inflatable exoskeletal devices, we may reconstruct the fitness landscape, the attractor landscape of the body as of your body, and we may reconstruct and influence this attractor landscape in such a way that it is again supportive as it were when the body was young. How does we implement that? Well, one way to do that is by virtue of inflatable elements. Here you see an attempt that we made to construct a support system for the knee joint. This support system for the knee joint that is not intended as a servo. It's not intended as a device that moves your leg, but it's intended as a device that follows the movements and influences the dynamic landscape of your knee joint in such a way that it again becomes easy to control movements in this attractor landscape. So, for example, small perturbations are readily damped out, transient times are reduced, and things like that. So it's really not the idea that this device doesn't walk you. This device makes walking easy. That's the idea behind it. There are many reasons to use inflatable elements here. Of course, inflatable elements are relatively easy to construct. They may be cost effective, so to say, cheap production. They may be easy to personalize. And probably the most important aspect is soft robots are safe robots. That is, I think, especially if you want to implement your robots in environments such as a hospital, it's really important that nobody can be hurt by that. And of course, a lightweighted soft structure is there really advantageous. Next point, here statistical mechanics. Spatial structuring of a chemical reaction environment may support the synthesis of branched oligomers. I want to explain what I mean by that. So, for example, assume you have a chemical reaction network and this chemical reaction takes place in one pot, in one reaction environment. Well, all these chemical reactions, they run based on the specific conditions, and it's quite probable that these conditions are not the same for all the reactions. Therefore, if you run your reactions all in one pot, the probability that you run them under suboptimal conditions are quite high. You have to find one fits for all conditions. These one fits for all conditions may not be optimal. So what is the obvious solution? Well, of course, you subdivide your reaction environment into different compartments, and in these different compartments you perform your reaction under optimal conditions. Sounds good, but there is also a con to that. Of course, if you do so, you have to organize the transport of matter and also information between the different compartments. There have now been several European projects trying to implement that. I want to give you a first idea of how we can apply a twofold optimization step when we work with compartments that are able to exchange molecules, matter and information. You see here, well, also only as a sketch, you see here and the idea is that this is a microreactor. You see small compartments. These small compartments, by a first optimization step, can be divided up into several types of compartments, each of which performs a specific reaction under optimal conditions. Now you have a first optimization, but now by arrangement of this compartment you can do a second optimization step. Second optimization step, because if you choose a specific arrangement, what will happen is that if a reaction takes place in a blue compartment, the products of this reaction, if spatial structuring is applied, will necessarily go into a green reaction compartment and only then enter a red reaction compartment. Therefore, you can somehow bring in a sequencing, as a sequences, a time order into your chemical reaction. Why is that important? Well, assume that you want to construct complicated branched molecules, for example oligosaccharides. Well, oligosaccharides can be constructed by use of something which is similar to click chemistries, specific linkers, but specific linkers, it's not like DNA linkers of which you have a combinatorial variety of different types.
Rudy, can I ask a quick question?
Please.
What are these molecules good for?
Sugars.
Why?
Well, sugars.
What are they good for? Just so we have a bit of an idea.
Cell signaling. Cell signaling, they also play a very important role in the immune system. Actually, these sugars, these complicated sugars, they are, for example, important in the structure of cell adhesion molecules. And they are one of the ways how cells communicate. Glycoproteins are, well, one of the languages with which cells do communicate. And only now glycoproteins and oligosaccharides became important, because only now we are starting to understand how they can be formed. The problem is, as soon as something is branched, it becomes difficult to synthesize it. Linear molecules are easy to synthesize, but branch molecules, that is much more difficult. So, these oligosaccharides, they are difficult to construct. The reason is that the linkers between the components of these molecules, you have different ones, but it's not a combinatorial variety. So that means if you assemble them, if you just bring together the individual components in one pot, and if you stir this pot, well, there will be some molecules which are composed in the right way, but there's also the possibility of side reaction, which decreases the total yield of your reactions, of your output. So, at the Artificial Intelligence Lab, Benedict Reller investigated a system which is composed of chemical containers. We call them containers. These containers are arranged on a two-dimensional substrate. The containers themselves, they are linked together via DNA linkers. These DNA linkers are highly selective, and with these DNA linkers you can construct a spatially structured reaction environment. And in this spatially structured reaction environment, you form your branched polymers. And as a matter of fact, it turned out that that the yield of the desired molecules can be heavily increased as soon as you include a spatially structured, or as soon as you use a spatially structured reaction environment. I have to point out, it's a geometrical structuring of your reaction environment that influences the way and the order of reactions in your system. Another approach, also done by an AI lab member, mostly by Matthias Weiland, is something different, a different system. It's called the Magit automaton. It's based on ideas of Doran Lance, by Doran Lancet, Steen Rasmussen and John McCaskill. It's a system that, again, can be composed, but it's intended to be an automaton, a machine that can be built. For the details, I refer to the paper that is given below here. And the interesting thing about this magic automaton is that Matthias Weiland was able to give a compiler for the automaton. As a matter of fact, the automaton consists of a one-dimensional stripe of different types of compartments. In these compartments, different operations can be performed, and Matthias Weiland was able to write a compiler that takes as an input a branched oligomer and spits out the order of these compartments. I think it's to some extent a rather nice work, or very nice work, because it's the first real chemical compiler that has been shown for branched molecules. Finally, I would like to point out the idea that cells should be regarded as dynamical systems and not only as reaction vessels for a given chemical kinetics. For example, if you study a process like endocytosis, endocytosis is a relatively important, or is quite an important process in transport between cells and also inside cells. There is a specific reaction is important. This is Rab5 Rab7 conversion. The details are not important here. The important fact is that this process happens on small vesicular lipid-bound structure called vesicles, especially called endosomes. You see here on one side just the chemical kinetics, but now, Nathan, if you can start the video. We studied this process in some details. And you see here, chemical reaction it's not only chemical reaction that takes place. What you should focus on is the fact that it's important that the green spheres have to be close to the green spheres, and the yellow spheres have to be close to the yellow spheres. Do not worry about what they really are. The important point here is that the morphology of these objects play an important role. Can I go back to the presentation? The important lesson we learned from these studies is that when you want to understand cellular dynamics, it's not sufficient just to understand the chemical kinetics. It's also important to take into account the dynamics of supramolecular assembly of aggregates, molecular aggregates, and also membrane dynamics. The interplay of all these different dynamics finally constitutes, a network of interaction. Here we use the network picture, and this network picture of cellular dynamics is to some extent rather important, or is very important. It's presently the way how people look at cells. But if you take into account that the fact that the system really operates is based on the fact that there are attractors in the dynamic landscape of this reaction network, then you realize something, I think, and not only I, but also others think, something quite important. There are two superfamilies of dysfunctionalities of a network. Of course, one way you can destroy a network is by destructing for example, one node of such a network. Then it will not anymore function properly. Another way of destroying this network is, of course, you bring the network into a wrong basin of attraction. That then means that the individual components of the system work well, but the whole system is in a wrong basin of attraction, probably performs not in the way you want. Why is that relevant? Well, you see, in earlier times, cells were just regarded as reaction vessels in which complicated kinetics takes place. In 2007, there was a very famous paper by Mel Greaves, and Mel Greaves pointed out that human beings are surprisingly vulnerable to cancer. In earlier times, people said, well, okay, we have mice. Mice is less vulnerable to cancer. Why is that? Well, mice don't smoke. Mice are small, so there are not so many cells that can turn into tumor cells. And of course, mice do not live very long, so complicated forms of cancer cannot develop. But then people started, and this is no joke, started to scrutinize elephants. well, sometimes elephants die in zoos, and they analyzed the dead bodies, the corpses of these elephants, and they found out that, well, in these elephants you don't find many tumors. So, interestingly enough, elephants, which live long and have a lot of cells, they are not as susceptible to cancer as we are. Why is that? Mel Greaves came up with the idea that, well, if cells are dynamical systems, then they are governed by attractor landscapes. Elephants live the way they should live, or the way they have been evolved for, but we humans, we permanently live under conditions for which we have not been evolved. So it's no wonder that from time to time our cells fall into the wrong basin of attraction, and that is one of the reasons, only one, but one of the reasons why we can develop cancer. And as a matter of fact, there's a lot of work done now in that field. I would like to point out Marco Villani and Roberto Serra, which studies cells from a dynamical systems perspective. And also we, at the University of Applied Sciences in Zurich, we try to understand, for example, this strange effect here. If you irradiate cells with X-rays, then interestingly enough, you would expect that the higher the intensity of the radiation, the more cells are killed. Actually, this is not really true. What you observe is here. What you observe is a little shoulder sometimes, or in a specific range. If you increase the radiation, then you decrease the killing rate. To understand this effect is rather important for the optimization of therapies, and well, we are using concepts from dynamical systems in order to understand better what's going on. So, finally, that's my last example. It's also a little bit a speculative one. There is presently a lot of discussion about a field called Psychoneuroimmunology. That means basically the interaction of the psyche with the immune system. And I think it's fair to say that the jury is still out. We do not really know whether there is a real interaction. But I think from an engineer's perspective, it's rather plausible to assume that there is interaction. Why? Well, you know, the immune system is a chemical system. The chemical system knows quite precisely what is going wrong. But it doesn't know where, or not precisely enough, where something is going wrong. Whereas the neural system probably does not know what, on a chemical basis, is going wrong, but I know pretty well where I have cut myself in my finger. So, from an engineer's perspective, it's rather plausible to connect, to merge this information. And I think here we should take into account the lesson that we have learned from Rolf. Again, Rolf pointed out that morphological computation and control does not mean that it's complete dynamics of the body, and it does not mean that it's complete digital control, but what we have to find is the optimal balance between implicit and explicit control. And I think if we bring in this point of view into the study of psychoneuroimmunology, then probably this field may profit from the engineer's viewpoint. So, I come to my summary. I think what I wanted to show you is first that by the application of external exoskeletal mechanical means, you can reshape the attractor landscape of elderly people. That may help them, that may re-establish the morpho-computational power of the body. Then spatial structuring of chemical reaction environments influences the way how reactions are orchestrated, and that may increase the yield of specific reactions, especially in the very complicated field of the synthesis of branched oligomers. Then the dynamical perspective, the dynamical systems perspective on systems such as cell may give us a further insight in different types of diseases and how to treat them and how to optimize therapies. And finally, maybe an engineer's perspective may be reasonable and worthwhile for fields such as psychoneuroimmunology. So, thank you very much. That was my contribution. Questions?
Thank you. Okay, is there any questions? Any questions? Yeah, we have one question here in Plymouth.
I have a question. At the beginning, you were talking about cells as dynamical system, but at the end, you are treating the neurons as another thing, not cells. Because in my opinion, the neuron system and the cells, they are all one dynamical system. So why you split between a chemical dynamical system and a binary one?
Yeah, well, very good question. Thank you very much. Well, as what I wanted to express there, that's the following. In the human body, you have different types of information processing systems. One is the neural information processing system, the other is the immune system. So that's a little bit like in our robots, where we have the body that contributes to computation, and of course we also have a controller which contributes to computation. And what I wanted to express in this last example is that if you want to understand how these systems work, it's probably sensible to think about the optimal division of labor between two different information processing systems with different capabilities. Of course, I do not deny, of course the neural system is also based on cells, but it's doing something different.
Okay.
Rudy, so can I also ask a question? You are often referring to the term dynamical system, and so implicitly you're talking about things like self-organization. Now, on the other hand, we have our robots, or the robots that we want to build, and we want the robots to do what we want them to do. So isn't that kind of a contradiction between self-organization and control?
Well, to some extent, that's a good question, a very good question. And frankly said, I do not really know the answer. But see, I would answer in the following way. If you want to cook a potato soup, then of course you could explain in all details how this process has to be performed. And as a matter of fact, I tried it. If you try to cook a potato soup in a chemical lab, you will experience surprising difficulties if you use the tools that were available in the lab. It's the way how when a good kitchenware really supports, probably in a self-organized way, the way how, for example, this convection of matter and the complicated, what is really going on in a pan? That's right. That's a very complicated chemical process. It's the fact that kitchenware has been evolved over, let's say, 200 or 500 years. I don't know the history of kitchenware. What I want to say here is that kitchenware optimally supports your cooking process, such that if you want to describe your cooking process, you don't have to refer to a very long list. Most recipes, it's completely sufficient to program to describe cooking programs by recipes no longer than one page. So, using the right tools, using the right let's say, devices, that allows you to shrink down the size of your programs. Recipes, but there's still a combinatorial variety of recipes, but they are all comparably short and surprisingly incomplete compared to what is really going on. You can reduce the amount of programming that you have to give, but you rely on the properties of the tools you use. And I think that's a little bit the same, or that's to some extent comparable to what you do when you build good robots. What you want to do is not describe everything to the last detail. Really good. It would be really good if you just could, well, describe what is going on and to rely on the properties of your robot, such that, for example, you don't have to explain in detail what uneven ground is, but you can say, well, walk over uneven ground. and the dynamics of the system makes it easy to walk over uneven ground. So self-organization shall support you. It must be clear where the self-organization starts and where the programming has to be. It's important that self-organization does not mean that you don't have to program. This probably, as all metaphors, cooking may not be the best one, but you see, in cooking, there is a huge variety of different possibilities, but it's quite clear what is cooking and what is chemical processing done by the structure of your pan. And if you don't believe it, try to cook in lab glassware, and you will experience how difficult that is.
Okay, thank you. Any more questions? Okay. We're a little bit behind schedule, so maybe we should thank the speaker again.